Yes, you are co-host now. Okay, so there was a long delay. So before the delay, I think we ended up writing partition functions for peptide sequences. Okay. Uh, for sequences. Okay, and especially helix coil transitions. Okay. Okay, so now you are familiar with the terms sigma and S. Sigma is basically for helix initiation, and S is for helix propagation. Right? So these are the elementary weights for. So if you have a sequence, C for coil and H for helix. Okay, so elementary weights for C is 1, and for the helix residue just after the coil is sigma S, and for any other helix it's only propagation, so it's S. Okay, so these are the three terms we familiarize, and for any given sequence or for any given configuration you can actually write the partition function. Okay, so now for a given peptide sequence many different configurations are possible, so we have to write the total partition function. Okay, so the total partition function also we did. Okay, and quickly what we have done, just highlight, it's a long time, is that the partition function for any given configuration is you have sigma and then S. Okay, so S is basically, let's say, if there are I helical residues, so then you have S times I, and then sigma is basically if you have j number of helical stretches, then you have sigma j, and then any degeneration. Okay. Okay, so this is what we have written last class, and then we have also done some simple treatment. Let's say finally, if you are interested in a fraction of residues, okay, fraction of helical residues in a given sequence. Okay, so basically, let's say I. Okay, so then that will be an important parameter. So then you would know that, for example, let's say given 40 amino acid sequence. Okay, so roughly how many acids, amino acids are in helical stage? So that would be an interesting element to know, so that you will give you idea about the structure of the peptide. So how would you get that? Basically, okay, so average, not fraction, average number. Okay, average number of helical residues. So basically I. Okay, so then you can actually define I, average I. Okay, I is nothing but so you have I multiplied by Ij sigma j si sum over then So more without I. Sigma over j and then S power I. Okay, so that's basically the definition for the average number of residues which are in the helical stretch. Okay, so this we can relate it to Q. Okay, so if you calculate, let's say, dou Q by dou X partial derivative, so then you get j sigma j S I minus 1 multiplied by I. Okay, so to get to this, okay, so you can actually divide so this, let's say, multiply by S, okay, and then divide by Q. Q is again Ij sigma j S I. Okay, so this is nothing but now is I bar, and then this side is S by Q, Q by dou S. Okay, you can also write this as S dou ln by dou S. That's nothing but I bar. Okay, so if you know the partition function, then by knowing S, if you know S as well, so then you can actually get the average number of residues in the helical stretch. Okay, so that will be an important parameter. Okay, so for that, so we need to know the partition function Q. All right. Okay, so to get the exact relation of Q in terms of, let's say, sigma and S. Okay, so we can start like this. Let's say you have an n segment peptide. Okay, peptide. And then for that, let's say you need to get partition function for n. Okay, so we can divide this into two segments. Okay, Q NC plus Q N H. So here all the configurations. Okay, so all the configurations where the rightmost residue is C, and this one is for rightmost residue is H. Okay, so partition function of the molecule where rightmost residue, okay, residue is C, okay, coil, and then the remaining are only two choices. You have coil or helix. We are talking about coil helix transition, and then this is for, let's say, when rightmost residue is helix. Okay, so by just dividing the total partition function into this and this, so now we will see that how to actually get this and this if we know these individual ones. Okay, so how to build this. But now imagine, let's say, to this n segment you add another residue. Okay, residue at the terminus. Okay, so if you want to add another residue, so let's say this n segment has whatever it is. Okay, C, C, H, C. Okay, so now, so that's your nth residue. Now you want to add at n plus 1. Okay, so what are the possibilities? Let's say now you have only n segment. Now you are adding one more residue.
It will be
So
either
the
C
next
or
residue
H.
can be,
Either
okay,
C
so
or either
again you
H.
have, yeah, either you have a coil residue and you have a helical residue. Okay, so if we know, let's say these two, okay, this is a partition function for Q. Now, so if you add one more residue, then the partition function will become Qn plus 1. So you have two possibilities. Either you can add a coil or you can add a helix. So by doing this, so we are actually changing, if you already know Qn, how to get Qn plus 1. So once you know this relation, you can always build however big polypeptide chain. Okay, so it will be easy. Okay, so Qn has two parts. Rightmost residue could be C, right? This is for Q and C, but here it could have H as well. So then for that the partition function is this. So for each one, now you have two possibilities, adding a C or adding a helix. Okay, so we do this step by step. So let's say if you add, let's say you have a coil at the terminus, and then you add, let's say C. Okay, so you already have a C. So if you add another C, so what will happen to this partition function? What do we have to multiply this to get?
Only one will be multiplied for another term.
So what is the term we add? We have to add. So this, okay, so plus what is the term it will be added? So remember, if it is coil, then the weight is 1.
1, yes, sir.
Yeah, so we are adding only coil. So then you don't have to do anything. Multiply QNC by 1 only. Okay, QNC. But now let's say you add H. Right? So what will be the term, corresponding term?
Could be another S multiplied.
Sigma S multiplied.
Okay, so yes, we need to do very careful. You see, easy because the weightage is 1. So you multiply this partition function with 1, you get this. Okay, so this is for C. Now, let's say if you add H, okay. So some people are saying yes, okay. Some people are saying sigma S. Okay, so which one is correct?
Sigma S will be there.
Sigma S.
S or
Sigma S.
so it should be, you need to keep an eye on the previous residue. If the previous residue is coil, then if H is coming, so you are initiating a helix. So if you are initiating a helix, you need initiating parameter as well. But if the previous residue is H, then you don't need to initiate. Already helix is initiated, you just need propagation parameter. So for this case, so because the previous residue is coil, so you need to initiate a helix. So you need sigma and as well as propagation S. So you need to multiply Q and C, okay, with sigma S. Okay, so that is when the previous residue is C. Now let's say imagine previous residue is H. So then you have partition function now, Q and H, okay, for this entire N segment. Now again you have two possibilities, C and H. So when you add the C, again the weightage is only 1. So just you multiply by 1. So you have Q and H. But now let's see if you add H. Okay. So what are the possibilities now? S or sigma S?
Only S will be there.
Only
It is
S.
propagation.
Previous residue is helix, means that helix is already initiated. So you don't need sigma and you need only S. So then Q and H multiplied by S. Okay. So this is for C, this is for H, this is for C, this is for H. Okay, so now we worked out, if you already know the partition function for Qn, how to get the terms, adding one more residue to make it Qn plus 1. So you can actually write this as a simple 1 sigma S into Qnc plus 1 plus S into Qnh. Right? Okay. So just like in the case of Qn, we divided the partition function into two parts, where rightmost residue is C and the rightmost residue is H. We can do the same thing for Qn plus 1. So how to divide these terms into groups? The terms which have the last residue as C and the terms which have last residue as H. Okay, so that we can do. So let's say if you have to do that, Q n plus 1 C and Q n plus 1 H. So of these four terms, we have four terms. So which terms will go into this part, where the last residue needs to be C?
The QNC part and QNH part.
So which term will have C?
The QNC part and
QNC.
the QNH part.
Okay, so this term will go here. QNC. And then this term will come here. QNH. And this term will go S U N H. Okay. Okay, so this is clear. Okay.
Yes.
Yeah. Okay. So now when we started Qn, now we got a beautiful expression for Qn plus 1. So once you know n and n plus 1, so basically you can really solve this method from one residue to nth residue and n plus 1, right? So let's put this in more meaningful, okay, mathematical forms, okay? Like let's say matrices here, because you have two terms. So you write, let's say Q n plus 1 C and Q n plus 1 H as a matrix, okay? So this is basically 1 by 2 matrix. So then you can write this in terms of Q and C and Q and H. Okay, so you have these two terms giving rise to these four terms. So what will go here? Okay, so you are taking basically Qn partition function parts and then converting into, by adding one residue, you will get n plus 1 parts. Okay, so these two terms, now you can really think of, this one is nothing but these two. It's basically 1, 1. So this, okay, no, this multiplied by these two will give you Qn plus 1. So basically QNC plus QNH is this. And to get the Qn plus 1 H term, so you need to multiply QNC and NH with sigma S and S. Okay. So 1 by 2 matrix, 2 by 2 and 1 by 2. So by multiplication you will get 1 by 2. So Qn plus 1C is QNC, Qn plus QNH, Qn plus 1 H is basically sigma s multiplied by this plus s multiplied by this. Okay, so this is good. Okay, so now, so this is n. So to get n plus 1 from n, you need to multiply by this matrix. Okay, so let's call this as m. Okay, so to get n plus 2, you need to multiply basically n plus 1 by this. Okay, so like that, you can now write a generalized form from let's say a residue 1. So we started n segment, and then we added n to get n plus 1. Okay, so it's the same thing. Now you can in principle walk backwards, and then you get from residue 1 onwards. So when you have only one residue, so it could be just a coil residue or the helical residue. Okay, so it's not meaningful practically, but mathematically it could be C or H, right? When you have first residue. Okay, so the state for the coil is 1, 0. So how to actually write this in terms of basically from the page. So you can write so in terms of matrix n, let's say if you start with, okay, imagine let's say this n. Okay, so you get basically q 1c and q 1n. Okay, but then if you do this n times, okay, so then you get qnc and then sorry qnh. Okay, so if you apply this method n times by residue 1 at a time, you will actually get this partition function for the n segment, okay, peptide, where you can divide the terms into last residue is a coil or helix. It is. Okay, but Qn is basically sum of these two. So Qn is basically Qnc plus Qnh. So you can actually write again another simple matrix. Okay, so that's basically the partition function for, okay, where simply simplified into a simple matrix, okay, algebra. The weights for the helix initiation, okay, assuming that elementary weight for the coil is 1. Okay, so using that as a simple matrix, you can really get the partition function for this. Okay, so far it's clear. Any questions? Can you guys hear me? Someone say hello.
Yes, sir. Hello.
Yes, sir.
I think. Okay, good. Okay, so what's important is that in this helix coil transition, by assuming, okay, few assumptions, simple assumptions, okay, simple assumptions, we can really assuming again only 2 states, coil or helix, and then once the helix propagates, helix can continue very easily, okay, and simplifying all the complicated factors like helix means that assuming that hydrogen bond formation. That means
Sir,
certain
your
stabilization,
internet connection
okay,
is very
and
poor.
is weak?
Yes, I also can't see anything.
Okay, is it?
It's very blurry.
You can't.
Yeah,
Oh.
it's very blurry.
I see. So bandwidth is low.
Yeah.
Okay, is for everyone it's an issue
Yes.
or only
Yeah.
for
Yes,
Yes,
for
sir.
everyone.
Yes, sir.
I'm writing, sir. That's a really large letters.
Still we can't see.
Sir, actually the voice is breaking also. So is it hard to follow the steps?
Okay, now voice is break. Hard to follow what I'm saying. Okay, I can't really do anything. The screen is freezing. Same. Okay, well, I'm talking slowly. I don't know what else I can really do. Okay, but let me see. Has followed this, so because this is an important thing. Okay, so this partition function, finally writing in terms of a simple matrix containing elements sigma and s. Okay, so one can write this. Okay, so the question is that, so then how to actually minimize this m? M we have written in terms sigma and s, but still we need to, it's good to have simple expression for q in terms sigma and n. Okay, so now because now we have converted this into matrices. Okay, it says that my internet connection is unstable. Okay,
Sir.
it's back now. Okay.
Sir.
Yes.
Sir, how this column
Yeah.
matrix 1 0 is coming? Can you please repeat that? I did not follow at that time.
Oh, okay. So you have to start with, let's say, one residue. Okay. So either you can write, let's say, you can actually start writing from, let's say if you have only one residue. So what
Okay,
are
sir.
the partition coefficients? Okay. So partition coefficients will be Q1C, that residue could be coil or helix, right?
Yes, sir.
Right.
Yes,
So
sir.
now you have, let's see if you put n in the case of n1, so then you have Q1C and Qn. So that will be basically 1 plus sigma s.
Yes, sir. Yes, sir.
Okay, so you get from 1 plus sigma s. So once you build first residue, so then we learned that how to add one more residue. Okay, so Qn is this. So then how to actually simplify now for m power n. Okay, so that's the question. M power n. Okay. Yeah. Yeah.
Yes, sir.
Someone has.
Yeah, I have a question. Can you hear me?
Yeah. Go ahead, Mithil.
Yeah. So what is the reason behind the assumption of the starting matrix to be the starting vector to be 1 0? That is, you start with a coil only and not with a helix.
No, it's not like that. So the state is okay. So you can write. Let's say we are not really assuming anything. So let's say only one residue. Okay. So it could be in coil or it could be in helix, right? So you have to write the partition
Yes.
functions for both. Literally write, let's say 1C and then 1H. And then if you do this matrix 1, 1, sigma S, so what you will get 1 plus sigma S, right? So those are the terms for this. Okay. So that's basically that. Q1C plus Q1H. So we are not really assuming anything, but we have written kind of state matrix. Okay. So you will get this expression. So you have both elements. We are not really assuming that the first residue are one segment peptide. We are not assuming either coil or helix. We have both terms once you substitute in this. Okay.
No, but
Metadev, got
then
it?
what is the reason for that one?
So both terms are there.
Then this. So
I
So I-
don't know if
so my
anyone can hear me. Metadev, say something.
hello,
I think
your voice is
Metadev,
breaking.
I cannot hear. I know, it's the same both ways. I also can't hear your thing. I'm not sure where is the problem. Let's say for a moment, I'll just put video off. I'll hear only your question. Okay, Metadev, can you hear me now? I just put my video off temporarily.
Yes, I can hear you. So is my voice clear now?
Yeah, now it's better.
Okay. So the question that I wanted to ask is for a system with no residues, you imagined the number to be
Yeah.
1, 0, the vector where you are representing that if it's a coil or a helix. So is it just because it fits mathematically, or is there a physical reason behind?
No, I think it's for mathematical reasons, but if you see, again, I'll put my video on. Okay. So once to complete the mathematical picture, okay, so you have a time, okay, but it's a 2 by 2 matrix, okay, so it's basically, yeah, 1 by 2, 2 by 2 matrix. To get only 2 terms, so I'm multiplying by 1, 0. But by doing that, I'm getting both terms, okay, Q1C as well as Q1H. So if you multiply this, you get terms 1 plus sigma S. So 1 is for Q1C and sigma S is for Q1H. Okay, so it will fulfill. So we are not really assuming that one residue system is only coil or only helix. Both are we are fitting. You understood this point?
Yes.
So how to get, the next question is that how to get m power n. So we know m, and we have to basically multiply this matrix n times and get a solution. Okay, so I'll just give you only simplified steps, but Aditya can do entire derivation, so which will take like half an hour, maybe 40 minutes. So maybe he can do, I don't know, tomorrow or after 2 days. I actually do this with you. Okay, so let's do this. So once we have this, okay, Qn in terms of how to simplify Mn. Okay, so in matrix algebra, there is something called diagonal. So then you can actually treat that as an eigen problem, and then diagonal elements will simplify and give you the values of that system. Okay, so here we do the same thing. So assume you have a matrix, okay, and you can find matrices, okay, such that find another matrix such that, okay, so M is a 2 by 2 matrix. So you have 2 other matrices, so T and T inverse. Okay, so this is basically multiplicative inverse of T. And if you multiply in this order, T minus 1, okay, inverse, multiplied by M, multiplied by T, you get a diagonalized matrix, okay, say gamma here. So which will have only diagonal terms, okay. This is kind of a diagonalization problem. I hope Ravi is going to teach you in mathematical methods this matrix algebra, diagonalization, and
Sir.
etc. So here,
Sir.
so we have a matrix M. Yes.
Sir, is it like the
Yes, there was
eigenvalue problem?
Yeah, it's an eigenvalue problem. It's
Hello,
exactly
sir.
that. Okay, your matrix
Okay,
Basically,
sir.
you diagonalize that.
Okay, sir. Okay.
Okay.
Sir.
So,
Okay, sir.
so basically, for any m, you can actually find t and t prime such that you will get a diagonalized matrix, and here lambda 1 and lambda 2 are called eigenvalues. Lambda 2 are eigenvalues. Okay. Eigenvalues. So once we have diagonal matrix, then if you want to multiply the same matrix because you have doing matrix do. So then
So video and
okay,
voice
so
both are breaking.
I know, but that's why I'm talking very slow duration.
So I
Okay.
can't see anything
So
literally.
Qn, again we write 1, 1, same thing.
Sir, we cannot hear you properly.
Yes, but you should be able to follow very slowly. Okay. So I'm simply multiplying T inverse T is nothing but identity matrix. So you can always multiply. Okay. So by an identity matrix, so which doesn't really change anything, like mathematics, multiplicative identity 1. You can multiply any number by 1, it doesn't change. So similarly, I'm putting T inverse T, okay, after M, again T inverse T M, so on and so forth. So this is nothing but that expression. Okay. So then you have T inverse T and okay. Sorry, okay, so this is one, okay, so T minus.
Sir, you are totally frozen right now.
I know, but I don't know what to do.
It's not possible to follow even if you speak slowly. It's getting worse.
But you're on. Okay, so at least can you follow this? So I have here m power n. I multiply t prime t inverse m t inverse m, so on and so forth. After last m t inverse and 1 0. So is it
Sir,
everyone
after the
follow till
square
this
box, I
step?
could not follow anything. Sir, up to this
After the
matrix
square
element
box.
1 1.
No, I'm not. See, I'm rewriting this. Okay, so
Up to
rewriting
that I
this,
could follow, but after that I could not.
but then I'm multiplying only identity matrix.
Now it has become clear. Now your internet is connection
I'm
is back.
multiplying only identity matrix. TT inverse is back. Better, Aditya? Okay, good to know that. Okay, everyone can hear me now, right?
Yes, sir.
Clear to
Yes, sir.
everyone.
Yes, sir.
Say
Yes, sir. Yes, sir.
Okay. Okay, good to know. Okay, so now you club all these things. T inverse T and okay, so this you can write this is nothing but the lambda. So now you will have
Sir, can you repeat the
now
part
you will have
multiplying 1 1 and 1 0? Is it again frozen?
Yes.
I think so.
Yes, yes.
Yes, yes, yes.
I didn't follow from the time.
but I'm multiplying with this identity matrix. T inverse T, or you can write T inverse, whatever it is. Okay, T inverse is I. So you can always multiply with identity matrix, okay, wherever you want. And then here
Sir,
I'm doing
you are
that
frozen
T
again.
inverse I.
You were frozen again. पूरा ही चला गया.
Can you now? Connection is unstable. Hello.
Yes, sir.
Hello,
Yes,
sir.
sir.
Hello, sir.
Hello, sir.
Hello, sir.
Okay, okay. So again, just I repeat couple of steps. So this we have already done. Partition function for n is nothing but multiplication of three matrices. Okay. So these two are intact, 1 1 and 1 0. And m power n is what I am treating here. Okay. You take a matrix T inverse MT is equal to lambda. That's one expression. And TT inverse is actually identity matrix. Okay. So because this is an identity matrix, you can always multiply these matrices with TT inverse. So I'm doing 1 1 as it is, but then I'm inserting TT inverse, then 1 m. Before the next m again, I'm inserting TT inverse identity matrix. Like that I'm doing between every m till the last. And then at the end, I have 1 0. Okay, same as before. Is it clear so far?
Yes, sir. Sir, I have a
Hello?
question.
Okay.
Hello, sir. Sir, I have a question here.
Yeah.
Why are you diagonalizing
Yeah,
this?
yeah.
Actually, why are you using this TT
No, no,
inverse
it's-
to multiply with the M?
No. See, you have your original matrix M. Let's say if you have to multiply that M
Yes, sir.
times. Okay. So each time, let's say
Yes,
for
sir.
one segment, it is only N M and I. It will be easier. Okay. So you have only diagonal elements. So that will be simple qualitative, simple multiplication without any, without having
Sir, again
complex
you were frozen.
matrix multiplication.
Sir, you
Okay.
were
So
frozen
now
for
let's say once you write this, again, no way.
sir, you
I
were
think people
frozen
can
for
hear
a
me, others
second.
can hear me, maybe some connection. Well, I have reconnected, right? Okay, so I hope you guys can hear me now. Okay, so once you have this step, so I'm just now looking at the terms like this. Okay, so T inverse MT. So you have n such terms, and each of has only diagonal elements λ1 and okay. So this one can be solved very easily. So this is what basis. Okay.
Sir, I have a question.
Yes. Yeah.
Sir, why you multiply
Yeah.
by the
Go ahead.
front? Hello.
Yes. Go ahead.
Sir, why you multiply the 1-1 matrix before? What is the necessity of that?
No, so that you will have gamma. Okay. So that you can have these terms. So basically you want to have T inverse on the left side of the M followed by T. Again, for every M you want T inverse. So in essence, you need to insert T inverse between two M. Okay. For the first one, you need one more T inverse, so that's why you inserted T inverse. Okay. So let's say once you have this, so this can be okay. So once you know the gamma, you can
Sir,
actually
can you,
solve.
sir, can you pronounce the final
Sir,
expression?
sir,
The screen is too blurred.
Sir, I am asking that the 1-1 matrix, not the T inverse.
Okay, I'll pronounce this Q and
No, sir, not that. The lambda one.
function for N,
Sir, the lambda one part, not that. The lambda one expression.
lambda 1.
Yes, sir. Just below that. The lambda one, just below the that. Yes, sir. Yes, sir. Yes, sir.
Still
Yes, sir.
writing. Okay, I'm still writing. Okay, I'll write big ones.
Okay, sir.
Okay, so I haven't really finished. Okay, so what you get is that, okay, so this term, so imagine now lambda is this n times. So you will have lambda power n and lambda power n terms. Okay, so if you solve that, but you will get final expression. Okay, so eigenvalues of n. Okay. So in terms of sigma and s, this is what you get. Okay, no need to memorize this. Okay, so everyone can see these two expressions. I read out lambda 1 equals 1 plus s plus in the square root 1 minus s square plus 4 sigma s. 4 divided by 2. Lambda 2 same as lambda 1 except the sign is reverse. Here it is plus, here it is minus. Everything else is same. Okay? Okay, so lambda 1 and 2
Sir, what is the sign in the root over part?
same.
Okay.
1 minus s whole square plus 4 sigma s. Okay, so we can again find out t as well. T inverse. Okay, so T inverse and so T inverse will give you
Sir, hello.
yes.
Sir, how are
Yeah.
you getting the equations?
No.
Sir, the
After
sigma.
solving,
the
so you know. I'll go upstairs. Okay. I'll go this one. So you can actually diagonalize. So you know what
Yes,
is
sir.
n? Okay.
Yes, sir. Yes, sir.
You know. Okay. Then so this is called diagonalization procedure. Okay. So you can start with a matrix. Okay.
Okay, sir.
Okay.
Okay, sir. Okay, sir.
And
Okay,
then
sir.
you can find inverse to get diagonalization. So this is called diagonalization procedure. Okay. So because
Okay,
we didn't
sir.
have math course,
Okay, sir.
I diagonalization. Okay.
Okay,
So
sir. Okay, sir.
now lambda 1 and lambda 2 in terms of variables s and sigma. Okay. And so this is t. So similarly, you can find out t inverse. Okay, I'll just write down. So they look very big, gigantic matrices, but this is simple. Simple matrix algebra. Camera 2. Okay, so m power n will be much easier. So finally, you will get q1, qn is nothing but 1 m power n 0, right? So this will give you beautiful expression in lambda.
Sir, can you please pronounce what is written in T matrix? It is
Yes,
not
sir. We
visible.
cannot see this properly. So T and T inverse both.
Oh, yes, I got it. Yeah, both. Yes, because yes. Okay. So matrix T inverse T, you have lambda 1 minus S by sigma S. Okay, minus sigma S and sigma.
Sir, your
1
voice was frozen in
minus-
between.
Voice was frozen in between. Okay, I'm repeating. T lambda 1 minus S by sigma S, lambda 2 minus S by sigma S, 1, 1, and T inverse matrix 1 over lambda 1 minus lambda 2, and the terms are sigma S minus sigma 2, sorry, S minus lambda 2 minus sigma S, sigma lambda 1 minus S. Don't worry. So I'll actually, so this I'm doing from Mayer and Jackson. So I'll give you the chapter number. I think I have the PDF copy in the Google Drive, right? So you can actually look at it. Okay. So the problem is that board, the dust is already, I don't have a cloth here. So if I have a cloth, because that is again making it not visible properly. Okay, so once now you know the diagonalized matrix, and then you have a row matrix and column matrix. So if you multiply, you will get a single term because Qn is basically a simple expression, right? So that expression looks like this. Okay, I'll write lambda 1 power n plus 1 minus lambda 2 . Okay, a simple expression containing the terms lambda 1 power n plus 1. Okay, because we have n power, right? Okay, n times this. Again, it says my internet connection is unstable. Okay, let me write this. Hello.
Hello, sir.
Okay, I am back. You can hear me?
Yes, but you,
Yes,
see,
Yes,
but
sir.
the screen is frozen. The screen is frozen.
Your screen is not visible, sir.
Yes, sir.
Times. So what you get is that an expression which has power.
Sir,
Is the screen visible? Is
sir,
The screen is not
screen is
visible.
totally stuck.
The screen is not visible.
Sharing
So
the
I
motion
understand.
from
Sir, it does
past
not, the
The
screen is
band-
not moving, sir.
It's the bandwidth problem, bandwidth. So it's like low bandwidth, so that's why it's not able to resolve. Okay, just let me know once it is visible. Hello.
Hello, sir.
Hello, sir.
Yeah. Okay. So I'm not doing much. So I have written just one expression. So M is a diagonalized matrix with eigenvalues lambda 1 and lambda 2. But now if you simplify that matrix multiplied by n times, you'll get a single expression for Qn in terms of lambda 1 and lambda 2. If you see the overall power, lambda n plus 1, okay, and lambda 2 n plus 1, but of course we have to know the partition function in terms of just if you know the eigenvalues lambda 1 and lambda 2 for any n segment partition function, so you can actually get this. Okay, so this is the expression. Okay, so after taking out all the matrix algebra part again. Okay, but so this becomes even simplified.
Sir, sir, just a small query, sir.
Okay, yeah.
Sir, how you experimentally measure this S value? Like how we know what is the value of S for the propagation initiation? Yes, like
No. So that's what is basically in theory. Now you estimate. Okay, so now you have experimental values, and now you vary the parameter S. Okay, value, and then see that for what S value you will get the experimental value. So now in the next class we'll compare how S and sigma vary. Okay, so if you vary S and sigma, okay, how
Okay.
does basically how does basically the helix propensity will change? Okay, in n segment peptide is what we will see. But for today's class, so this is the expression for Qn in terms of lambda 1 and lambda 2. But if you make another simple assumption, lambda 1 is larger than lambda 2, so then more or less most of the terms actually will get cancelled, and you will get approximate Qn is directly proportional to simply the n power of lambda. Okay, so by doing this, you can really see that how simplified the expression will become. And so we measure in the beginning of the class. So average, okay, average number of helical residues, right? I bar. We have written S by, okay, so R fraction, okay. So S by N is dou ln Q by dou S. Okay. So we know the lambda in terms of their S and sigma values. So you have Q. So you can find out the partial derivative of this with respect to S. And then that will give you directly the average number of helical residues. Okay. But the question is that, so how does S and sigma will affect, okay, so the propensity of helix, we will see some values, okay, how sigma and varying sigma and S will vary the propensity, we will see in the next class. Okay,
Sir,
I think today's not bandwidth is not
Okay,
correct.
sir.
sir, I have a question here. When we are
Yes.
solving this eigenvalue, we are getting the lambda 1, lambda 2 as the eigenvalues. So what is the basis of
Correct.
choosing lambda 1 greater than lambda 2? Why are you
No, no,
choosing
no.
this
So
lambda
with
1 greater
that
than lambda 2, not the other way around?
Okay. Yeah. So now, no, we will see lambda 1 and lambda 2 are not identical. Okay, let me see if I have expressions I have written, right? So you can really see from the values itself. Okay. So you see the lambda 1 and lambda 2. The main difference is here it is you are adding two values.
Yes,
Here
sir.
you are
Yes, sir.
subtracting.
Yes, sir.
Okay. So all quantities are positive here, sigma and S. If sigma and
Yes,
S are
sir.
positive, so your lambda 1 is always larger than lambda 2. Okay? Because
Got
it's
it,
a
got it,
positive
sir.
negative sign. On that basis,
Sir, another thing is
assume
that,
this is greater. Yeah. Okay, go ahead.
sir, in this case, the lambda 1 and lambda 2 are the eigenvalues of this equation. So, is there any significance of physical significance of lambda 1 and lambda 2, or they are just a numbers we are getting?
No, lambda. See, lambda 1 and lambda 2 are eigenvalues of a matrix.
Yes,
Physical
sir.
significance is
Yes,
for
sir.
S and sigma. Okay? Yeah.
Okay, sir.
Lambda
So
1 and
they are just
lambda 2
numbers, right?
themselves,
Lambda 1,
they don't
lambda
have
2.
any physical. They don't
Okay,
represent
sir.
any
Okay, sir.
physical quantities. They are combination
Okay,
of sigma and S. Okay. So next class, so we will see basically this one. Okay.
Sir,
So how it might be useful, but this one sigma and S. So then you can actually use that as basic parameters, S and sigma. Okay. So imagine like we assumed very simple theory. So we assume that the energy of or the weightage of coil is 1. So with respect to that weightage, we are calculating sigma and S. Okay. And only two parameters we have. So with the two parameters, we are actually now a generalized theory for helix coil transition of a peptide as big as possible, you know, so n, you just have to really substitute n. So now we will see, let's say how exactly this n will play an important role in terms of a given peptide, okay, size dependent, okay, how does that size and the values of S and sigma would vary where how much fraction of the peptide is going to be in a helix or coil, because this coil helix transition is actually very common, which can be studied much easier compared to any other complex secondary structure.
Hello.
Hello, is sir here? Still?
No. Rita is host now.
Is the class over?
I guess let me call sir. Class is over. You may leave.